Okay, so we would like to show Young's inequality to actually present it because, as we're going to see, its proof is a couple of pictures. So, in any case, imagine that we have a function f. So let f from 0 to infinity to r be non-negative, or rather, I could say strictly increasing. So continues to make it more immediate, strictly increasing. With f of 0 equals 0. Then we have the following inequality. If a comma b are greater than or equal to 0, then ab is less than or equal to the integral from 0 to a of f of x dx plus the integral from 0 to b of f to the negative 1 of y dy. Of course, it's silly to put y dy, but when we show the graphical interpretation, I think it will make sense to keep our variable as y. So the idea here is pretty simple. So we have a strictly increasing continuous function, and we take two random numbers, a and b. So here's a and here's b. And then we're saying that if we take the rectangle, then that's less than or equal to the integral of the function f from a to x, which is this one, plus the integral of its inverse function from 0 to b. And you can, of course, see here that this is the case. It's just shown graphically. And of course, there are a couple more cases that we could have here. So in particular, again, let's say that this is our function. And let's say now that, oops, here's A and here's B. So this time around, we have this kind of situation. So here's A, here's B. So now the integral of the inverse will be exactly that. Whereas the integral of the function itself is going to be this one. Okay. And of course, we can see that in this case, we also have the inequality, obviously. Finally, we also have the case where A and B completely align. So A comma B is on the graph. And in this case, obviously, we have equality. Of the product AB and the two integrals. Now, if one wants to have a more rigorous interpretation of this, one can even build Riemann sums. So let me just show you how we could start with here our function. And let's say that this is A and up here it's B. So if I start building the lower Riemann sum for F, then it will look something like this. And now it's interesting to see how this precisely corresponds to the upper sum for F to the negative 1. So they line up completely, and you can reach, once you reach the first point, then you will see that a lower sum from 0 to A has completely lined up with the Riemann sum for F to the negative 1. And then there is the other functions, the other rectangles that we get past B. Oops, sorry about this. The other rectangles that we get past B are giving us the extra area that eventually forces the inequality. So in other words, if we take Riemann sums for this two integrals, then those Riemann sums are completely going to cover the rectangle with dimensions A and B. And that is going to show that as the partitions get finer and finer, the corresponding Riemann sums tend to a number, actually, as they have right here, their sum is precisely the value of the two integrals, and it's larger than the rectangular area. So that would be, for example, one way to give an analytic proof by choosing specific partitions. And also the nice thing about this is that one has to show it in one case, because the other case is pretty much symmetric to the first one by changing F into F to the negative 1. But I hope that the graphical interpretation is more convincing than everything else. And we would like to actually use Young's inequality for a specific case. And the specific case is the case where we have f of x equals to x to the p minus 1 for a number p which is greater than 1. This is exactly the case where this function is going to be strictly increasing and has f of 0 equals 0. So in this case, we can ask what is the integral from 0 to a of f of x dx? And the answer by simple calculus is that this is a to the p over p minus 0 to the p over p, of course, which is a to the p over p. Now, we can ask now what is the inverse function. And as usual, to find the inverse function, we set y equals x to the p minus 1, and we solve for x. So the inverse function, so x is equal to y to 1 over p minus 1. So the inverse function is y to the 1 over p minus 1. So if we want to take now the integral from 0 to b of f to the negative 1 of y dy, then we will have the integral from 0 to b of y to 1 over p minus 1 dy. And this is equal to the antiderivative will be y over 1 to the p minus 1 plus 1 over 1 over p minus 1 plus 1 from 0 to b. And of course, this is going to be y to the, b to the, now p minus 1, 1 over p minus 1 plus p minus 1 over p minus 1. That is going to be p over p minus 1 over p to the p minus 1. And now we have a very interesting situation. If we set q to be equal to p over p minus 1, then we have the interesting relation 1 over q is equal to p minus 1 over p, which implies that 1 over q is equal to 1 minus 1 over p, or rather that 1 over p plus 1 over q is equal to 1. So this becomes b to the q over q. So now we can state the ultimate corollary that we need from Young's inequality. So if p comma q are greater than 1 with 1 over p plus 1 over q equals 1, then a to the p over p plus b to the q over q is greater than or equal to ab. And this is really what we would like to use in order to prove Hölder's inequality and subsequently Minkowski's inequality. And that's all. Thanks for watching.